Start going through some of the novelties. So we're gonna, you and Steven are both technical guys, but you kind of approach things a little bit differently. Steven's really, focused on that front end technical with the specifiers as his, main function amongst other things. But Saad, you actually get with contractors more so on a daily basis. So we kind of gave you the field stuff, the stuff the contractors need to know. And hopefully you can help us apply that to why it's important. Starting with squeeze off tools. Now, squeeze off does happen in other markets. You can squeeze off other types of pipes, but HDPE, it's very different on the way we handle it. So basically, all we're doing is we're occluding the pipe, and that lets us stop flow. So in a repair setting, if you cannot actually access a valve or something of that nature to stop the flow of the line, it's very difficult or impossible to repair. So all gas utility contractors, they carry these squeeze off tools because gas is dangerous, right? A fire can be very deadly. So if they can't access a valve, they always have this as an option. So we're basically just pinching down on the pipe to stop flow, and that can be really helpful, like I mentioned, in the repair application. Now,
And it's driven primarily by HDPE's viscoelastic behavior. Is you're allowed to, you can condense it. You're not at risk of cracking it. And that's really what allows us to do it.
yeah, I'm really glad you mentioned that, Saad, because it's not necessarily a standard. There is a PPI bulletin on how to squeeze off HDPE. So there are rules you want to follow, and it's because that viscoelastic nature that HDPE wants to recover. So we control how long it takes for us to pinch it off, and then also on the release, how long we release that pipe itself. So the gas industry, they assume that you damage the pipe, and they tell you to put a band clamp on there. Not always necessarily in the water market, but I would say it's probably a pretty good approach if you guys wanted to be conservative and assume your contractors or crews out there are not properly taking the time to observe it. Maybe they're in a hurry and they're just closing it off as quickly as they can. Live tapping. Do you want to take live tapping, Saad, or you want me to?
Yeah, so live tapping, and Dan, feel free to chime in whatever I miss. It's really, a question we often get asked by pipeline owners that say, "Hey, can we connect service lines to an existing line that we have, or rather, can we connect branched outlets to an existing service line without taking the service line out of service?" And the answer to that is yes, you can. There are different ways that you can do that. There's no one right answer for every solution, but just as a quick example, you say you want to have you have a 12-inch water main and you want to connect a branched outlet, which is 6-inch. You could electrofuse a saddle or attach a mechanical saddle directly on top of that and hot tap that line, assuming you have a valve at the other end connecting to that saddle. Those are really the examples of where live tapping is often utilized, particularly in the waterworks industry that we see quite a lot of. But it again comes back to the versatility of the pipe that you can use it for. And again, there are different solutions, so I'm not going to say one solution is the best for every situation.
Yeah, great point. Also, I love the small diameter, maybe even medium up to 10 inches. It's very easy to tap with the self-tapping tool, whether it be electrofusion or mechanical. However, when you do get in the higher ends of the medium diameter and especially your large diameter pipes, you will then start tapping it the same way. So your stainless steel tapping sleeves, same way you're already tapping ductile, PVC, anything like that on that larger equipment.
That's correct.
Allowable bend radius?
Yeah, absolutely. So bed radius, the reason I actually took the slide was I think this is probably the biggest commercial value that polyethylene has compared to legacy pipe materials. Again, when we come back to polyethylene's viscoelastic nature, polyethylene can be bent into tight configurations and environments to navigate different obstructions on site. Now, the really, really neat thing about it is that when you bend polyethylene, it's not at risk of breaking or cracking. It's more at risk of kinking, kind of like a garden hose. And so the limitation that you see in the table for the bend radius for polyethylene is really driven by the resistance to kinking that polyethylene displays. And a good example that I can provide you here is if you take a thicker walled polyethylene in the same outer diameter the bend radius for that thicker wall is actually smaller than the bend radius for the same outer diameter with a thinner wall. And again, it's not because of the risk of cracking it, it's more risk of kinking it. And so this really allows us to reduce fittings on site. It allows us to navigate all kinds of obstructions we might see, and it allows us to manipulate the pipe through terrains and topographies that we may not have had the foresight to conduct initially.
Yeah, absolutely. And we're going to get into maximizing productivity a lot more on number 9. However, when you start thinking about things you actually are able to do to a pipe, so a great point. This is kind of one of the many reasons, right? We can really maneuver that pipe as easy as your job site allows, right? You've lesser
Now, one thing that
conditions.
was sorry, one thing that would be really important to talk about the previous slide. This assumes a fused monolithic pipe system. If you introduce a mechanical coupling within this pipeline, you are now going to limit your bend radius to whatever deflection that coupling can handle, which oftentimes is not a lot. So really, really important to note out that this is a fused monolithic system.
Absolutely. Good distinction. Locating HDPE is definitely, I call it a novelty, but PVC, same issue. Really, anytime you're getting away from a metallic pipe, you're either going to want to use a tracer wire or these 3M marker balls. The tracer wire here, this is a pipe burst that they're doing, and you can see that spindle on the left-hand side is just they're pulling that copper line in as they pull HDPE, and so you would never want to bury an asset without being able to find it. And with plastics, they are more difficult to locate. So we do put these copper wires just right next to the pipe so that we are able to, if we need to identify that at a later point in time, maybe we need to mark that utility because we're putting a nearby gas line in or something like that. These 3M marker balls, you can see them on the right-hand side. They're using open cut, a little bit more difficult in trenchless, right? Because you got to get it somehow into that trench. But we like those as well. The nice thing about those, you can program as much information as you'd like into them. So basically, it's an RFID signal. So you can program what type of line it is, what the burial depth is, when it was installed, who installed it, etc. No preference between the two, just something for you guys to consider when you are specifying your projects. Oh, above ground behavior. This is certainly interesting. Do you want to start us off with this one, Saad?
Yeah, certainly. I think there's a 2% carbon black that's added in and that's added to the polyethylene polymer. If you've actually seen a virgin polyethylene polymer, it's actually transparent. It's not black. So the manufacturers actually add 2% carbon black to provide an indefinite amount of UV protection, which allows us, again, more leeway when we're constructing our projects. There's no special storage facilities within which they have to be contained. They can be left outside in the sun indefinitely. And it's actually one of the biggest reasons that polyethylene is used industrially above ground as well for a lot of clients.
Yeah, that's a great point. I think I've told this story in the webinar program, so I'll keep it brief. We became good friends with a gentleman in Washington, D.C. that does Engineers Without Borders. And he told me that, his project's moving forward. He wants to use HDPE, and I was really excited about that. But the main reason he ended up wanting to use poly was sometimes when you're shipping jobs to these, impoverished countries, you're not always certifying that pipe instantly gets installed. So with other pipe types, you can have issues and those warranties can expire. It's not necessarily suitable for potable water after it's been exposed to the elements for an extended period of time. And then trenchless is definitely a major distinction. So can you kind of walk us through how it benefits us in both trenchless, but also in rehabilitation projects as
Yeah,
well?
certainly. So again, we're going to tie this back to the bend radius for polyethylene. Polyethylene is a viscoelastic pipe material, so it can withstand substantial axial and circumferential strains. And so essentially, with the viscoelastic behavior of the pipe, we're able to install it in a lot of creative ways, a lot of them being trenchless. So with trenchless, there's two main ways that we see it being utilized in the polyethylene world, and that's HDD, which is horizontal directional drilling, and pipe bursting. So horizontal directional drilling, kind of as what the word says, it's really installing a new pipeline within an environment within which you can horizontally directionally drill. So you have a laydown yard, you're fusing the pipe. As you're fusing it, a hydraulic winch is actually pulling the pipe into the ground where it needs to be placed. Now, in the situation where you already have a pre-existing asset, such as a failing cast iron or a concrete pipe system or whatever you may have, which is compatible with it, we can actually attach a pipe bursting head to the hydraulic winch and have the polyethylene trailing it. So it uses the same methodology as horizontal directional drilling, except now you're actually breaking the old pipe asset, fragmenting it rather, and allowing the polyethylene to take its place. So you don't actually have to build a trench to remove all of that pipe. And you're already using your existing right of ways, so you don't need new permits from the city that you're building it in, because the owner already has the permits to operate their pipeline asset within there.
Yeah, I like how you in your head categorize them by installation method. Today, just having a conversation in Atlanta, a gentleman came into the booth looking at pipe bursting, but it's in the switchbacks on these mountains, and it's always under the roadway, which rehabbing pipe under roads can be very difficult. You have to shut down arterial roads a lot of the times. So there are a lot of factors that can push a project either towards HDD or pipe bursting. A lot of times we think we're going to rehab it, but a new installation with some of the methods we have are still often the correct solution. Even though we don't necessarily think of abandoning and drilling a new line as a rehab project, you're still maintaining that asset, even though you're changing it over. That's becoming quite common as
With
well.
static pipe.
Expansion and contraction. This is so Saad, you give a lot of lunch and learns. This is kind of how we got teamed up and one you were doing up there in Ontario. This has to be the question when you go in the office you get before
Yeah.
you even sit down at the room, right?
This is what we often get is perhaps one of the biggest scares that engineers display when it comes to specifying polyethylene pipe. And so this is a two-part piece of information that I'm going to kind of talk to you guys about. There are two characteristics that you want to be aware about when it comes to polyethylene pipes. And those two characteristics are your coefficient of thermal expansion, which is your middle column, and your elastic modulus, which is your right-hand side column. Now, what happens is polyethylene, for every delta temperature change for the same OD as, say, carbon steel pipe, is going to want to expand and contract more with every delta T. So if we take the example right here that we have for a length of 200 feet, 2-inch DR11 polyethylene pipe, for a delta T of about 40 degrees Fahrenheit, the polyethylene is going to want to expand about 8 inches, whereas the carbon steel pipe is only going to probably expand about 3/4 to 3/5 of an inch. Now, however, because the elastic modulus of polyethylene is so small compared to metallic pipe systems, the force required to actually prevent that thermal expansion contraction is substantially smaller, because the force required to prevent that expansion is directly proportional to the elastic modulus. And so when we actually crunch the numbers, you'll actually find that the force required to prevent that expansion of the polyethylene pipe is only about 321 pounds of force, whereas the carbon steel pipe, you're looking about 8,000 pounds of force. And so the reason that this is important is when you have buried polyethylene pipe systems, the ground typically offers enough forces around it to restrain that pipe to prevent any expansion or contraction blocks. The only place that you need to pay close attention to the expansion contraction is, one, if the pipe is above ground, or two, if the pipe is terminating at a rigid end connection above the ground. And there are very small ways to design for that, which we can talk about later. You're on mute, Dan.
Thanks for not letting me get too far. Yeah, that's always a good one to jump ahead of. And kind of what we say with the thermal expansion and contraction is just make your final tying connections the next day. So, if you're doing a pipe burst on Tuesday afternoon, make your final tie-in on Wednesday. That pipe could pull out from the grouted, that low strength connection at the manhole. So we really just ask for those final tie-ins to be the next day on those big temperature swings. There's also expansion and contraction that occurs in some of these slip lining or HDD applications where we're straining that pipe so much that we could slightly make that wall thinner. So when you elongate the pipe, you could draw out the pipe wall. So the good rule of thumb, or the best rule of thumb I've heard, is to allow that pipe to relax for the same amount of time it was held under tension. So if it took you 3 hours to slip line a project, or 4.5 hours to pull it in for an HDD drill, the same amount of time it took you to pull it in at 4.5 hours, give it 4.5 hours after the drill to let that pipe relax or come back to its final thermal and mechanical equilibrium. So kind of what that looks like. most of the time on these rehab projects, whether it be a slip line, an HDD, these are where your handoff points typically exist anyway, Sod, right? With your GC. This is, a specialty contractor most of the time, is what you're seeing on these projects.
Yeah, typically that's kind of where your handoffs are. But like kind of like you said, you just have to make sure you give the pipe to allow it to take its average temperature overall.
Awesome. Yeah. And this picture kind of is really the main talking point. And it really illustrates it well, I think, because all we're doing is creating a handoff point and kind of a sequence of events. Just let that pipe relax, and you're really not going to have any issues. Just they have an MJ adapter on the end of here, so I know they're either terminating to a valve or back to a legacy material. But they also closed up. They put a bag around this pipe as well. So this is definitely an experienced HDPE contractor. But for those less experienced, we get a lot of questions on how to make in-ditch butt fusions, or more so, people just ask us, how do we make in-ditch tie-ins? Can you kind of walk us through the thought process on that one?
Certainly. So, well, two questions there. There's can we do in-ditch butt fusion? The short answer is yes, we can in-ditch butt fusion because we have certain fusion machines where you can actually remove the carriage off of the fusion machine and place it into the ditch where the pipeline actually needs to be fused. We've fused 48-inch in ditches as well. Again, no real complication in that process or anything like that. The only thing you always have to make sure of is that the site is clean. That's really about it. Now, the second question you talked about, Dan, time. The time really depends again on how much space you have. What are you trying to tie in? Because you have the option of using in-ditch butt fusion, but then you also have 3 other options. And so what our goal really, particularly the distributors that you work with, is to look at how you're trying to tie that into your existing pipeline and then recommend solution 1, 2, and 3 to educate you about the different trade-offs.
Yeah, I like the distinction you made. I should be evaluating it more so as options, right, or tools in your tool belt
That's correct.
than a one-stop solution. And
That's correct.
these in-ditch butt fusions, right? Because they're a good solution. Electrofusion is also done from time to time on these tie-ins, and of course, mechanical connections on
That's correct.
different industrial applications are quite common as well.
That's correct. And there's trade-offs to all 3 of those. So it really just depends on what is it that you're trying to achieve. And that's something that we typically talk with our customers about to get them the right answer.
Absolutely. And just to kind of, finish out this talking point, this is where working with your preferred distributor, this is kind of the expertise that they can provide you. We get a lot of these questions, as you know, and I pretty much reach out to you guys quite often and see what you recommend in these situations because things vary, a lot across North America. So, um,
Absolutely. And that's a critical point, Dan. A solution that might work well for an oil and gas client designing an above ground tailings line is not the same solution that's going to work for a water main customer in another geography. So, as a polyethylene distributor, one of our biggest goal is not just providing the pipe, it's really providing the right solution for how you're going to connect that asset. Sometimes you want your pipe to last 10 years, and some customers want their pipe to last 100 years, depending on what their project constraints are. And so we really take all of that into consideration before providing you the right answer.
Absolutely. So yeah, modern, if you reach out to your pipe manufacturer, they'll put you in contact with a preferred distributor if you guys don't already have one. And the alliance can help you act as an intermediary as well. And then, we talked about productivity and a couple of different things and bending radius saw. Can you kind of walk us through what, what aspects of HDP really do lend a helping hand to productivity?
Yeah, certainly. So what you're seeing right now, really, maximizing productivity is really just building on the physical and chemical properties we talked about earlier in the presentation. You can have long individual laydown yards and quite literally string the polyethylene pipe, fuse it, and then continue to drag the pipe on rollers because the pipe is viscoelastic. So you're not having to be delicate, or you're not having to delicately handle the pipe the way you may do other legacy pipe systems. So, there's some really, really cool pictures, which, we can send Dan, and Dan will show us later in the presentation as well, where as the pipe is being joined, the contractor is literally just stringing the pipe along. So you got this massive length of probably 300-400 meters of pipe that's just being dragged along the road. In fact, one of the biggest reasons polyethylene is used above ground for industrial clients, particularly oil and gas and mining, is because they like to leave all their pipeline assets above ground, and they don't want to have to support it the way metallic systems, for example, may have to be supported every 20 or 30 feet. So that's really how you maximize productivity. You're not spending a lot of time or cost on how am I supporting my asset as I'm using it and dragging it along. That's kind of
Absolutely. The
what
one
I
last
think.
thing I wanted you to touch on is I often when people are designing, especially trenchless applications, they don't necessarily look at laydown and staging. Can you just touch on laydown and staging really quickly and kind of
Certainly.
framing people to where they
Lay
start?
down staging quite literally, as long as the pipes are the weight is distributed normally on the on the pallets they're placed on. You can put them anywhere. You can put them outside. You don't have to cover them at all whatsoever. It ties back to the point that Dan made initially, where there's really no substantial cost required in how you store the pipe, as long as you're not putting too much weight on top of the pipe, which you have to take care of any thermoplastic type in, you're going to be okay. So that's really what I can say from a laydown perspective. We can put it anywhere that we have leased land.
Well, fantastic. Awesome. Let's hop off for a little bit. We're gonna ask Steven to hop on and take us through some design considerations, and then we will go through some final talking points we want people to be aware of as they start designing. So, Steven, can you start walking us through the difference in pressure class and kind of some ID matching stuff that this is maybe becoming our most commonly asked question the last year or so?
Yeah, hey Dan. Um, yeah, this is probably one of the more confusing issues, and I don't know why that is. I think it's just because of the development of the materials over the different years and the AWWA standards that were developed from each of those materials as they evolved. So, the term pressure class is used in municipal applications. You see it all the time. It's not really used a lot in other applications, but pressure class is the mainstay of a design criteria within municipal applications. So for different materials, pressure class means different things. They're all defined differently. That's the one thing you need to understand. For materials like ductile iron and PVC, pressure class may not and usually doesn't mean that's the working pressure rating. As you go forward to polyethylene, though, you can see that because of the unique properties of polyethylene, the pressure class does usually equal the full pressure rating that system can operate at under high flow conditions. So there's a difference between static pressure rating and dynamic pressure rating, and that has to be taken into account and compensated for the particular application and project and design criteria for that project. So we got to remember also you see DR a lot, dimension ratio. We'll talk about that a little bit and define it here and how that corresponds to working pressure rating. And then you have the surge allowances that go along with that as well. So if you look at what DR means, so dimension ratio, do we skip that slide? Let's go back to that slide real quick, Dan. Sorry. There you go. If you look at dimension ratio, that is a definition. So it's the actual OD of the pipe divided by the specified minimum wall thickness of the pipe. So that's gonna dictate the stress bearing capability of that particular structure. In this case, a pressure vessel, and that so for every DR, doesn't matter what size a pipe is, we'll have the same pressure rating or stress carrying capabilities, whether it's half inch to 65 inch. But the same DR has the same pressure rating because as the diameter gets bigger, the wall thickness gets correspondingly bigger. So if you can see that from this size chart, so if you look at the various sizes of polyethylene, you'll see different. You'll see two columns rows at the top, pressure class and pressure rating. So again, like I said, with polyethylene, when you see the pressure class, it usually means the pressure rating of the product, even at high flow conditions up to 10, 12, 14 feet per second. Common DRs for polyethylene are 11, 13.5, even 17. We see them in larger diameters up to DR 26 all the time for municipal applications. So you can see there's quite a range of offerings and capabilities within polyethylene.
Yeah, so
So,
Steven,
yeah.
great points. Getting the surge pressure. I wanted to preface this before you give us the deep technical on this, but a few years ago, before I really understood the surges and velocity issues, I was part of my job is to evaluate specifications from cities across the U.S. And I started to notice there's a lot of design restrictions on velocity. And even more so, what I found interesting was that certain utilities even have different velocities for different pipe types. So they'll have one velocity for PVC and one for ductile as well. But I've never seen restrictions on polyethylene. So that kind of was very confusing, for someone that doesn't understand this issue quite well. So I understand where people are coming from in this being a complex issue. It is something to focus on.
Yeah, I mean, I agree with you, Dan. It seems complex on the surface if you're not used to considering it. But once you understand it and then just realize it has to be considered and just, design with that materials, best properties. And so that's the way you do with anything, right? So you just got to understand that polyethylene is going to be different than PVC or ductile iron when it comes to design. So you're right. Many municipalities have a maximum flow velocity that they want to design to, and there's really good reasons for that. So they have the everyday or everyday type velocities, which are normally lower, which they look at, and then they have like their peak demand velocities that they want to limit as well, because that has a huge impact on their system, and all the appurtenances and everything in that system can be affected by this water hammer or surge pressures when they do occur. And you have to design for that catastrophic event and make sure your whole pipeline and different valves and things like that just don't have problems handling that. So if you,
Stephen, as we start walking through, we already got a great question, and the way Tom asked it, I think, is probably the best way to define the issue that we are trying to answer. And he asked, "Do you specify internal or outside diameter?" Do you think that's typically the ID matching people are asking for when they're, addressing this topic?
that's a really good question. So my understanding, and again, I've been doing this for a while, that there's sizing systems, right? And they've been out there for a century, and we're just kind of going along with how those were designed. For pipe, almost exclusively, you're going to be dealing with OD. So when you call about a specific size of pipe, it's going to be specifying an OD size range, if you will. Now, that doesn't mean when you say a 24-inch pipe, I'm going to get a 24-inch OD. You would think it'd be that simple. And in some sizing systems it is, such as IPS or iron piping systems. Once you get above 14-inch, that size is actually that OD. For ductile iron pipe, though, ductile iron piping system, I'm not talking about the material itself, just DIPS sizing system, that OD will be different. So you really have to pay attention to that and understand that you could get an IPS OD or a DIPS OD, and they're going to be different.
Okay, I promise to stop holding you up. I just want to get this right before you start getting too deep in the technical. So I'm going camera off. Thank you, Stephen.
Oh, good point. No problem. Anytime these questions come up, let me know. So we talked about the surge. So anytime you have a flowing fluid, you're going to have potential for surge events. And so in piping systems, we want things to flow through them. That's just what they're designed to do. They're not designed to be a pressure vessel. They're designed to be dynamic. So with that becomes pressure surges. The magnitude of that pressure surge is going to be directly proportional to the modulus of the material the pipe's made from. So the same event, let's say 4 feet per second or 8 feet per second instantaneous flow change, that resulting magnitude of pressure spike is going to be different. You can see on the chart, the bar chart there, that for polyethylene, this is an exact same situation, 5 feet per second instantaneous stoppage in flow. You're going to generate 56 psi in flow in surge. That's on top of the working pressure. For that same situation for a PVC pipe, DR18, you're going to generate 87 psi surge event. For a ductile iron pipe, because it's so stiff and has such a high modulus, that same event is going to generate 255 psi in surge. Now, it's going to be an instantaneous surge, and it's going to be what they call a water hammer, right? So each of these things are going to behave differently. And then you have to look at the material's ability to absorb or to handle that type of shock. So every material is a little bit different in how it's designed for that. Polyethylene is because of its lower modulus and the toughness of this material, it can handle these recurring surge events much more easily. So for recurring, you're allowed to go 1.5 times the pressure class rating of the pipe. That means for 15 million cycles over the life of that product, you can go 1.5 times its full pressure class rating and not have any issues for cyclic fatigue or failure. For occasional, which means once a day, twice a day, something like that, you can go 2 times the pressure class rating. You can see for materials like PVC and ductile iron, it's going to be different. So you have to understand your system, how it's designed, and what those ramifications of those surges are going to do, and design appropriately for it. Don't take one material and design it the same way for everything. You won't get a good design. We talked about why is surge an issue. So surge is an issue for 2 things. First of all, you're going to get that pressure spike. That instantaneous pressure spike can cause some issues. The bigger problem, though, with surge is the cycles. So it's a repetitive cycles that you get from these surge events millions of times over the life of these systems, and what that's going to do to what we call the cyclic fatigue, or the fatigue failure for these individual materials in these piping systems. Polyethylene has shown to have over 15 million plus cycles without fatigue failure. For ductile iron, it's not really factored into design. So you just have to make sure you're well within the safety margins allowed for that product. And for PVC, you can handle some surge events and some cyclic fatigue, but it's going to be limited. As long as you take it into account, not a problem, but make sure you take it into account in your design. So this is from the, let's just, for an example, I'm not showing you how to design with these products. This is an example out of AWWA M23, which is the design and installation guide for PVC pipe. It shows you. So for instance, if you have a DR18 PVC pipe, that's a pressure class 235. For every foot per second surge or flow velocity change, you're going to generate 17.4 psi in surge. So for even 4 foot per second change, that's 70 psi in surge event that's going to happen. That may have to come off of that pressure class rating. So now that product working pressure rating may only be 160 psi instead of 235 like the pressure class. So ductile iron will be similar, polyethylene will be different. So you mentioned here for ductile iron, this is out of their design and installation guide, M41. For every foot per second change, you will have an increase in pressure by approximately 50 psi. That's pretty high. And so again, it's a strong material. It can handle it as long as it's designed properly and the working pressure is not too high. So you have the working pressure plus this surge has certain limitations you have to make sure you stay below. So if you get back to what polyethylene can handle, again, because of its toughness, because of its lower modulus and the viscoelastic, we'll use that word again, Saad, behavior of the material, it can readily handle these surge events over and over and over. So again, 1.5 times the pressure class rating for surge. So look at a DR11 polyethylene pipe highlighted there, has a working pressure rating of 200 psi and a pressure class of 200 psi. It can handle allowable surges up to 100 psi and occasional surges up to 200 psi above that working pressure rating. That's huge. That's a 14 foot per second flow velocity change that polyethylene can handle without having to derate the pressure class rating and working pressure.
Yes, Stephen. So just to make sure we're all understanding this correctly, we have a working pressure, and that working pressure does not have to be derated unless we are going past these high velocities, correct? So
exactly. In this case, for polyethylene, pressure class does equal working pressure rating, unless you're going over 14 feet per second flow, which most municipal systems won't. Some industrial applications might, but most municipal systems are limited to 8 feet per second. So you can see here, you don't need a PC 200, even though a lot of people use it. If you're operating at 125 PSI, you can use a DR17. Now, there may be other reasons you don't want to, But for pressure rating and surge capability, it can handle it all day long.
Yeah, so did you have a comment on that as well?
Yeah, just to build on that, this is really really important because oftentimes we see engineers selecting thicker pieces of pipe to accommodate a greater degree of safety. You don't need to do that with polyethylene, period. Particularly if you want a 1-to-2 safety factor ratio in your designs. In fact, before you commission the polyethylene pipeline, you actually have to, there's I forgot the name of the spec, Dan, but you actually test it to 1.5 times its max level working pressure before you commission your polyethylene pipeline. So you're already testing that recurring surge limit before you're operating it.
Absolutely. Yeah, we'll cover that in the pressure testing section as well. That's a good distinction to make. Yeah, thank you for answering another one of my questions.
So just to kind of summarize here a little bit. So for instance, flow velocities and pressure ratings. So for a DR14 PVC pipe, it has a pressure class of 305, has a surge allowance of pressure class times 1.6. Now that's going to be for occasional surges, not recurring surges. It's 0 above that for recurring surges. For ductile iron or class 51 ductile iron pipe, it's rated at 350 PSI, but that's for no flow. If you have any flow through it, 1 foot per second can result in a 50 PSI increase in pressure. And so at, for instance, 9 feet per second, you have no pressure rating left. It's going to be all taken by the surge. So you have to design for that appropriately and mitigate it. So for polyethylene, as I mentioned earlier, it can literally handle 14 feet per second flow without derating its pressure class. So a PC 200 polyethylene can handle a flow of 14 feet per second all day long, even if it's operated at 200 PSI working pressure, which municipal systems won't be. So you have a huge margin of safety you're dealing with there that you don't need to you don't need anything more for that. For DR13.5, it's even up to 12 feet per second. So there's a lot of information, I'll call it, out there about ID matching. And on the surface, it sounds very simple. But of course, as most things in engineering design, it's not always as simple as it appears once you start digging into the details. So you have a lot of things going on in a piping system. You don't have just pipe. You have fittings, you have valves, you have different types of appurtenances, you have changes in angles, and changes in path, and different things that are going on that are going to result in frictional loss of some sort. So just looking at the ID of the pipe and trying to say, okay, I have this ID for that, I need this ID for the same. You're not going to end up with a good design because it has to do with the frictional factor of the pipe itself, not just when it's new, but as it ages also. So the Hazen-Williams factor, what we call the C factor, the higher that number means the smoother that pipe is and the more capability it has to flow fluid through it without having a frictional loss or a pressure loss or a delta, we'll call it a delta P, if you will, through the system. So the higher the factor, the smaller the energy losses from water flowing through it, which, like I said, that's what piping systems are for. For polyethylene, with a fused joint in it, that has a Hazen-Williams factor of 150 to 160. We usually use 150 just to be on the conservative side. But that's over the life of the system. It doesn't change. It doesn't degrade. It doesn't change at all through the life of that system. So your flow capacities and the fluid carrying capacities don't reduce. If you look at things like other typing products, we'll just use cement lined iron pipe here for instance. Everybody realizes that over time that mortar lining becomes a little more rough, it degrades, and that friction factor will decrease, or friction factor increases, the corresponding C factor decreases. So depending on the age of that pipe, you're going to actually have less flow capacity, typically when you need more. I mean, these systems are put into place where you have certain needs for flow based on population and industry. And that usually doesn't go down. It usually just increases. So you want more flow over time versus less. And with polyethylene, that original C factor is never going to decrease. That's one reason why you don't need to match IDs to get equivalent flow. There's several others. That's a whole nother study by itself. Chemical resistance. Polyethylene is extremely well known for having very, very high chemical resistance to a whole range of chemicals. This is not normally what you'd see in municipal applications, but in industrial applications, you may see all sorts of things. There's a really good technical report put out by the Plastics Pipe Institute, TR19. It's available online on their website for free download. It has hundreds of chemicals in there, and the general resistance of polyethylene and even other materials to these types of chemicals at various concentrations and various temperatures. So if you have a unique situation you're looking at, I really recommend taking a look at that document. For municipal systems, though, we're really worried about disinfectants. So disinfectants, or oxidizers, if you will, are used to keep our water, safe, right? And so every material is affected by oxidizers in one way or the other. It just depends on what you're doing with it, whether it's a chlorine disinfectant, whether it's oxygen from corrosion for iron pipe. But I can tell you, every thermoplastic is affected by disinfectants. Doesn't matter what it is. It's going to be affected by that oxidizer when it's exposed to it long term. For polyethylene materials, we purposely now formulate those for long-term resistance to chlorine residuals in water systems. So this was probably a 5, 6, 7-year project where we looked at and developed models for how to qualify polyethylene materials to give you this 100+ year service life. And it uses a range of operating conditions: your average operating temperature, your average operating pressure, the residual chlorine, the pH of the water, what we call the chlorine resistance rating, or CC rating of the material used to make the pipe. And then also it's affected by size, so the OD of the pipe as well. Those are the factors that all go into it. And if you look at the next slide, you can see here that by taking these general factors and looking at general operating conditions. So for the average across the United States, 57 PSI ground temperature, water pH 7.75, disinfectant residual 2, 70 PSI working pressure. You can see that even a DR21 polyethylene pipe using a mid-range, a CC2 rated polyethylene, has greater than 100-year resistance to chlorine. Not going to be an issue. You go to even the most aggressive one all the way on the right-hand side. Let's say you're in an area where you have 80 Fahrenheit average annual temperature of your water. That's pretty warm. The pH is really on the low side, 6.5. The residual chlorine is on the high side, 4 ppm. Working pressure rating, 100 psi. Even for 4-inch DR11 pipe, using the mid-class CC2 range polyethylene, which CC3 is being the most resistant, even with that, you have well over 100-year design life of the product. So what I'm trying to get at here is you can look at your particular installation and operating conditions, go through the calculations. There's actually a great online calculator for this at hdpeapp.com. And look at, for your operating conditions, what is your disinfectant design life with polyethylene pipe? And I can tell you today, I haven't found any systems, operating systems today, that have less than 100-year design life using the CC3 rated polyethylene materials that are out there today. So chlorine resistance, you may have somebody's may told you that's an issue. I can assure you that issue has been resolved. And for the last 15 years, these materials have been in use and are doing extremely well. We talked earlier about restraint. So first of all, a fused polyethylene joint is considered a fully restrained joint. Once that is fused together, it's a monolithic system now. That 2 pieces of pipe that you butt fuse together now becomes 100 feet of pipe. There's essentially no joint left in that pipe. We all know this. It's a great benefit of polyethylene and putting long strings together that are never going to leak at those joints. They're not going to be the weak link in your system. But there are occasions where you have to connect it to other materials, of course. So you have MJ adapters, mechanical joint adapters, as you see in the picture here, which are very common, ductile iron pipe size, connect to any appurtenance, valve, hydrant, whatever you may have, fitting. If you need to use a ductile iron fitting, you can attach it right to it, just like you would any other MJ product. And then you also have traditional anchor blocks. So if I need to anchor it, polyethylene, as Assad mentioned earlier, has a little bit higher thermal expansion coefficient. The nice part about it is pretty easy to mitigate any movement, and there's ways to do it. You can use a butt fuse wall anchor in an anchor block situation. You can use an electrofusion flex restraint that you can put a number of those around the diameter of the pipe, how much pull out you're looking for design. Encase that in an anchor block design, and that will fully mitigate any type of movement that you need to connect that to a valve housing or wherever it might be, and not have any issue with the moving of the pipe. This also comes into play when you're connecting to other types of materials as well. So let's say you're doing a directional drill with polyethylene, put a new system in, and you want to connect to an old legacy system that's a bell and spigot, non-restrained situation. Well, the polyethylene is not going to be an issue. You don't have to worry about it pulling apart. But if you want to make sure that your bell and spigot pipes don't pull apart, there's two ways to mitigate that. You can put a thrust block in on the polyethylene and mitigate any movement there. But you should also put probably restrained couplings on those bell and spigot joints for usually 2 or 3 on each end, just to make sure that those don't pull apart either. So it's really not the polyethylene protecting, it's the old legacy systems you're protecting. But again, there's very common ways of doing that. If you want to look at anchor block design, how much do you need? Again, I would direct you back to hdpeapp.com. There's actually a new anchor block design in there. So what we've done is we've been able to go back through and now fully characterize the soil restraint that you have on a pipe and look at how much movement are you likely to get based on a certain temperature change. Whether, let's say, it's extreme cases of 40 degrees temperature change, how much force is that going to be needed to mitigate, and then you can design your anchor block for that. And this calculator lets you go through that and look at various scenarios just to see, all right, how much concrete do I need? How many cubic feet? How many how much rebar do I need in there? And how to offset it and things like that. So all that is in with this design situation. And again, it's very easily to mitigate that.
Fantastic. Thank you very much, Stephen. The design portion, like you said, it's simple topics once you understand, but if people haven't had the exposure to these topics, it's very easy to take what they are already currently designing for PVC and just tie that into
Absolutely. That's my one main takeaway. You're not going to learn it all right here. The one main takeaway I would ask for is just understand that polyethylene is going to be a little bit different in those respects. It has some advantages that you can take advantage of and really cut down the cost of your system. And if you over design it, you're just not doing anyone any good. Really take advantage of that and understand it. And I'd be happy to help out anytime.
Yeah, absolutely. And the earlier, if the designer does have those questions, the earlier we get involved, whether it be your pipe manufacturer like you or Sod or, my engineering team itself, it could save you a lot of headaches earlier just bringing us in. So
Absolutely.
Thank you very much, Stephen. Sod, if you want to come back
Thank
on,
you.
we'll start going through butt fusion. And like I mentioned at the beginning of the call, this isn't fusion training, but just kind of this is a main difference between other pipe types. So, what kind of training do we need? What does this process look like? When does it apply? That type of stuff.
Certainly. So really, butt fusion is what I call the unique value proposition or unique selling point of polyethylene. It's what differentiates polyethylene from most other thermoplastic materials out there. What you're seeing is in the video is you're going to have 2 pipe materials that are going to be, that are first cleaned and shaved to make sure you have pure virgin resin material ready to be heat fused. They're going to come together against a heater plate. that heater is going to form the appropriate melt bead. So just the right amount of melt layer that is ready to be fused together. You remove that heater plate, and then you are joining the pipes together. Now, the entire process of what pressure the pipes come together for, what time, et cetera, all of this is, dictated in the ASTM F2620 spec. But what's really important, the parameter that records all of this is the data logger. So what you're seeing right there in your screen is once the pipes have actually come together and that aqueous layer is fusing together, that is being fused together under, it's a thermal effect that's reforming the polymer at that cross section. So once the fusion joint is completed, that cross section is now the strongest part of your pipeline. And the main reason it's the strongest part of your pipeline is because at that cross section, you have the same polymer that exists throughout the rest of the pipe. So if you were to conduct a destructive examination and pull that pipe apart, it would not break at that fusion joint. It would break somewhere else along the pipeline. And that's really what differentiates fusions from other situations. I'm just waiting for the other slide to load here, Dan. Coming up. Is there anything that I missed, Dan, that you probably want to cover in the butt fusion process?
No, that's great. I did want you to highlight their differences. There is different equipment for different applications and kind of what that looks like. Obviously, you're involved in that selection process as contractor.
That's correct. Kind of what you're seeing on the screen right now, right? There are all kinds of different fusion machines as well. There's your manual fusion machines, typically for smaller diameters, 6 inches or 8 inches below. And then you've got your rolling fusion machines, which quite literally have, they say you can roll it along and manually fuse it at the same time. And you got your Trackstar, your T series from McElroy as well, which primarily just is very easy to operate. You quite literally push a button and the machine will roll. It's a hydraulic machine, and it'll clamp the pipes into place and actually bring them together as well. And then you got Talon at the bottom as well, which is for much larger diameters, but a very similar concept in general. What's incredibly important as well is the barrier to entry is not high. However, you have to make sure that your fusion technicians are qualified. The operators have to undergo certain certifications, that McElroy provides, as well as job site training, just to ensure they understand, the ways to operate the machines properly and what to look out for. And there are training courses provided to ensure people are certified inspectors. If someone else is doing a fusion machine, what are some of the key parameters you have to look for, particularly in the data log report, to identify if someone has made a mistake? Those are all critical from a quality assurance and a quality control standpoint. And they're very, very minimum costs. But if you want to maintain a pipeline and want it to last 100 years, these are very small steps to take.
Absolutely. And that training can be done by your preferred distributor or McElroy themselves. So there are some different options. Can you walk us through electrofusion and kind of the training options available for that process as well?
Certainly. So electrofusion, really, you're using coils that are embedded in the inner wall of specialized fittings. And what you're doing is you're attaching those fittings to the outer diameter of a pipe. So what you're seeing, for example, in the top right-hand column is a butt electrofusion fitting. You can slide, your pipe on either end. The coils from the inner diameter are mating with just the outer diameter of the polyethylene pipe. And so we can run a current to heat those coils up under a certain time, and that's going to melt the plastic. Again, same concept. You're going to fuse the plastic together. You're forming a monolithic joint. And again, you use them depending on what your application is. You're not always using electrofusion. You're not always using butt fusion. It really depends on what you're trying to accomplish here. And this is typically, the training for this is typically done by the manufacturers themselves. And then lastly, kind of what we're seeing over here, these are examples of mechanical fittings as well, mechanical and other electrofusion fittings. So electrofusion fittings, sorry, these are not mechanicals, I apologize. Electrofusion fittings can come in all kinds of configurations. So again, it comes back to what are you trying to achieve? So branch saddles, you want to connect a branch outlet. Threaded branch saddles, you connect to a threaded piece of pipe. Flex restraint, for example, is something that Stephen talked about earlier. when you're trying to control any expansion or contraction. So the flex restraints are electrofused onto the outer diameter of the pipe, depending on what your axial stress is that you are trying to mitigate. You can put 1, 2, or 3, depending on the OD of the pipe, and then you're just grouting it with cement to prevent any lateral movement. So that's just an example of where you can use electrofusion fittings. Now, mechanical joining, again, every item has a place and where it can be utilized. I saw a question earlier, which is, hey, how can we connect polyethylene to other pipe materials? And there are different mechanical connections depending on what it is that you're trying to achieve here. So just as a quick example, the picture on your right is on your far right. That's a George Fisher Waga multi-joint. That can actually be used as a transition coupling to connect HDPE to most other legacy piping system, whether that's PVC, cast iron, ductile iron, steel. Not only that, but a really, really big advantage of why we use that in the waterworks industry is it gives us an angular deflection of 8 degrees on each side of its connection. So a total angular deflection of 16 degrees. You might not get the same angular deflection on other mechanical connections. And so this is what we mean by one solution doesn't work for every situation. We really need to understand what it is you're trying to design for. It is a pricier option. However, sometimes when a client wants that angular deflection, it is the best solution to utilize. So there's lots of different solutions to what you were trying to achieve there.
Yeah, and great segue, Saad, because selecting your method for repairs as well, right? There's not really a one size fit all, but there are guidelines out there. There are pre-established standards on what that look like. And I personally, I know PPI prefers the electrofusion spool repair. I'm probably a little bit more lenient than most on the mechanical repair, but could you kind of just walk us, through what a spool repair looks like for electrofusion or mechanical?
Yeah, certainly. So kind of what you're seeing in electrofusion spool repair, right? You're essentially what you're doing is you say, for example, a contractor is cracked a piece of pipe and you have buried pipeline, which you can bring the pipes together to butt fuse together, but you want a fuse system. So in that situation, really what you're seeing in the picture is you're taking a pipe spool, what you call, and you have electrofusion couplings on either end. And then you're joining those electrofusion couplings on either end to the existing polyethylene pipeline. And you're essentially recreating your monolithic pipe system. And again, that's done when certain clients just don't want any metals or any metallic systems in their pipeline. So yeah, Dan, you can walk us through exactly what you're seeing right there. You're cutting out the damaged section, exactly what you're seeing. And this is actually a neat thing, right? You don't actually have to cut out the entire pipeline. You can see the crack right there on the right-hand side. You're just cutting out that damaged section individually and just recreating that spool. What you're seeing in the next one.
There's a few more steps in that electrofusion. You do to prepare both ends. So we're getting rid of that oxidation because we are fusing that pipe. So this step you would skip in the mechanical spool, but we're showing you what that looks like. We don't want to put a coupler onto a pipe that has not gotten rid of its oxidative layer. So by preparing that, we get rid of its oxidation and get ready to situate and fuse the coupler. So I like using this picture because it does show a relatively clean trench. And I'm not sure how often you guys get questions about these low water table clean trenches. So
Yeah,
like you mentioned, I do like the Waga.
Yeah, so this is more common when we're called in for waterworks repairs. This is probably a more common picture of what we see. Like I said, if you have a clean trench, like what you saw in the previous, then that solution works great. It works really, really well. That solution would not work as well in this particular type of situation.
And that's just kind of what you see with the larger diameter repairs. They're usually not full body couplers as often. I think the George Fisher goes up to 42.
Again, it really depends on what the client's trying to achieve, right? It really comes down into that as well. In fact, we're using some of these when we're transitioning, particularly to other pipe systems, quite often. But yeah, that's we're again, it comes down to what the logistics our time is and how long the client wants it to last.
Awesome. And then I do want to discuss the guided side bend test because that is a novel approach to polyethylene to wrap up the things we do differently. So actually being able to test that fusion, I recommend the guided side bend test because we are able to track 3 things at the same time. One, that we're using a qualified operator and he knows what he's doing, but also making sure that that equipment is fusing properly, right? Because from time to time, things do get out of spec. Your heater plate might need an element replaced. after 10 or 15 years, something like that. But also making sure that that pipe itself is fusing correctly. So just with this one guided sideband test, we're getting a lot of QA and QC out there on the project. So I just want to walk everyone through kind of what this test looks like, because it does take time. So I like to say specify this test, but don't ever specify, right? Because then you're giving back some of that productivity that you are getting by using polyethylene. So first step, obviously fuse that pipe, fuse that joint that we're going to be testing, and then prepare and cut those strips. So there are guidelines in that ASTM standard on how far we have to be away from that fusion that we will be testing. And we always want to make sure we're properly marking that equipment. So here we're kind of making sure the heater plate on that pipe. So if there is an issue, we know maybe it happened at 230, right? And we check the heater plate at both those points, the fusion pressures, etc. That can help us pinpoint and recalibrate the equipment if we did not get a successful test. So we want to make sure we're always tracking this correctly. And this is just kind of giving you guys some brief guidelines on how to prepare and test those strips to give you a feel for what that test looks like. But I'm going to go ahead and show us this video from PE Spotlight last year to show you really what you're looking at, right? So they fuse this pipe together. We're taking out a nice cross section. You can see all those lines. We're marking that pipe properly, making sure our samples are wide enough. But then we're going to actually cut out that test sample. And this is what that strip looks like as we prepare it. So basically just taking a chainsaw to both ends. And then from there, we're going to run it through a planer, right? Because we got to get that test strip down to a actual thin testable strip per that ASTM standard. And then once we have that strip, the actual sideband test is a relatively straightforward process. We're just loading it into onto this piston, and that piston is going to get us to a 90-degree bend. We're listening for a crack. You could pretty easily hear it, but you also want to take it out and check for it to make sure there was no cracking. So we can test a lot of the parameters, a lot of the things people are worried about by using a new pipe with this fusion process. It's really easy to test these parameters, but I do say specify this test. Don't ever specify it, right? We don't want to handcuff our contractors and make them do a 3-hour test at the beginning of every day, right? Maybe the rule of thumb, I guess I like to say, is your 3 parameters of fusion. So your operator, your pipe, and your equipment, test at the beginning of your project. But if any of those 3 parameters change, I would like to see another test, right? Because sometimes on these larger products, Sod, you'll have half your pipe from Pipeline and half from Modern or WL, whoever. So if you do have a pipe change, right, it's always good to make sure that pipe you now have on site is performing the way we want it to.
That's correct.
And then the data logger, that gives us a lot of QA and QC. Can you just walk us through kind of the capabilities of the
Yeah,
data
I'm gonna summarize this really, really quickly.
Yeah.
Just to be cognizant of time as well here.
Yeah, and we do have a full presentation available on this. So
For
kind
sure.
of just telling us its main
sure.
function would be
The
fantastic.
data logger is the equivalent of a black box on an airplane. Your operator is saying, hey, I brought the pipes in for this many seconds. I put it against this many pressures. Did they really do that? That's really what the data logger is reporting. It produces a graph of temperature against time. It tells the operator a lot of good information about how long they need to have the pipe together for. You obviously have to input a lot of parameters based on what the pipe size is, what specifications you're fusing to, all that good information, which Dan would cover in the data logger webinar. But really, it's one of the most important traceability controls that you can deploy, because the thing with HDPE is you can't non-destructively examine it after you've conducted that fusion joint. And so the data logger is perhaps your best traceability tool to verify the joint is completed to the ASTM F2620 specification.
Absolutely. And that's kind of the catch-all, right? This is really where you're getting confidence, regardless of the amount of control, right? Because you might not always have an inspector out there, but you can make them prove that every fusion was done in accordance. And that's pretty much all the new information saw. But could you, I know you want to tell us about one of these really cool projects you worked on and kind of tie in all the lessons you learned on that project.
Yeah. So we're trying to use a project here that demonstrates all the chemical and the physical advantages of polyethylene that we talked about throughout the presentation, and that's really what I want to summarize here. So a lot of what I'm going to tell you is public information. It's out there. You guys can Google it. One Google will tell you everything you need to know about it. But Toronto is actually home to the world's largest deep lake cooling system underneath Lake Ontario. If any of you have been to Toronto, there are 20 kilometers of 63-inch polyethylene pipelines that have been sitting there for the last 24 years. And this is what the process looks like. You have about 3 pipes that actually take water from Lake Ontario on a water treatment plant like that. Exactly what you looks like, 3 63-inch polyethylene pipes that are just sitting there at a depth of about 70 meters. They're pulling water in, and that water is going to a heat transfer station on Toronto Island. And then that's actually being converted and distributed throughout the city. So if we go to the next slide, I'll actually show you what that looks like. Yeah. So if we pause on this picture for a second, there's a couple of things I want to show you here. At the far right side of the picture, you can actually see that's where we're actually fusing the 63-inch pipeline. As we're fusing it, the pipe is being slung out, and it's actually placed on rollers. So remember when I told you you can actually fuse that pipe and bring it out, sling it out? Well, this is a representation of what that looks like. What you're seeing as well in this picture are concrete thrust blocks that are actually used to sink the pipe to its desired level of depth. And again, that's some engineering that the civil engineers take care of. And right here, the pipes, this is right before we're hydro testing the pipe, loading it off of St. Catharines in Niagara. Now, we go to the next slide right here. Again, we took 1 kilometer sections, floated them off outside, and we actually connected them together on an offshore platform. And the last picture of, if we go to the next part, Dan, this is really what I call the most important part of polyethylene. I want you to think for 1 second, out of all the pipelines that you've designed, which joint can handle a stress of what you are seeing on that pipeline right there? So every joint in that polyethylene pipe is fused together, and it's being pulled across a very large lake on a tugboat, and that's a 63-inch pipeline. So I want you to think about what kinds of axial and circumferential stresses are acting on that joint. And then I want you to figure out what pipe material can handle that outside of polyethylene. And that really is what I call the biggest selling point of polyethylene, is the integrity of the joint surpasses anything else that we have in the market.
Yeah, well said, Saad. A lot of those tools and all that design we do worry about, that does tie in. What does it culminate in? How are we getting productivity? What, changes are actually being made in the real world? And that cooling project, I know that's one of the coolest. That's gotten a lot of publicity for its success. So congratulations to you and your team. I want to thank my team, everyone that was on here today, the Modern Polymer guys, for sponsoring. If you have any questions, they are a tremendous resource. They can put you in contact with your preferred distributor. And any questions you have in the design process, we're here to help as well. Just to recap, if you guys are interested in PDHs, please fill out the survey when the webinar closes here at the end. If you guys have any information you guys would like to request, feel free to fill that out as well. And we will get that over to you all as soon as possible. And we just want to thank you all for attending. And we'll see you here with another webinar in the next few weeks. And hope you can all attend. Hope everyone has a great day.